Hey guys, just to let you know, this lesson is in collaboration with Flip Academy, a free online platform for all of your GCSE, A-level, IB and CBSE revision, out now on web at www.flip.academy, and also as an app for Apple, iOS and Android. It really is better than all the other GCSE platforms out there. It covers all the topics in great depth and has an app that you can download your courses on and use offline.
Hello everyone and welcome to Flip Academy. Today we're going to be looking at the numbers topic for the AQA specification. So in bold, what I have is every single spec point that you'll need. So as we go through it, we'll be able to check off everything that you'll need for your exams. So the first point says that you should be able to order positive and negative integers, decimals and fractions, and also use the inequality symbols, equals and not equal signs. So when you're talking about positive and negative integers, what you want to think of always is a number line. So we have, like, for example, minus 10, then minus 9, and so on. We would have 0 roughly here, and then it would go 1, 2, and then so on, 9, and 10. So if you were to draw this as a number line here, when you're ordering numbers, the side on the left is the smaller values, and the side on the right is the bigger ones. So what you need to do is when you're counting, think about that. And it's the same thing with decimals, okay? So for example, minus 9.5 being over here is smaller than, let's say, 0 or 1 or 2. So you should be able to look at integers and decimals and put them in order. So again, you can always use a number line to reference that. With decimals, you need to also think about place value, which we'll get onto a bit later on as well. But for example, something like 8.423 is bigger than something like 8.0523. Okay, and that's all about place values. Okay, and in terms of fractions, if you want to order them, it gets a bit more interesting because what we have to do is make all of the denominators the same. Okay, so as you can see here, we have 20, then 8, 4, 5, and 10. We can't compare fractions like this, so instead what we have to do is make the denominators the same. So what you need to do is look for the lowest common multiple between this. So what that means is I'm looking for the smallest number that all of these numbers are in terms of a times table. So if I look here, they all actually go into, so it won't be 20, but it would be 40. Okay. If you're ever unsure, it doesn't actually have to be the smallest number, it just needs to be one of the numbers. So if I look, all of these numbers will be able to become 40. So what I'll do is I'll write all of these in terms of 40. And what I need to do is think about what I times the bottom number by in order to get 40. So what do I times 20 by to get 40? Well, I times it by 2. Then whatever I do to the bottom number, so the denominator, I do to the top, the numerator. So I times this one by 2, 20 times the top by 2, that gives me 22 over 40. What do I times 8 by? Well, I times it by 5, so I need to times the top by 5, that gives me 25 over 40. Times 4 by, well, I times it by 10, so I times the top by 10. Gives me 30 over 40. And here, what do I times it by? I times it by 8, so I times the top by 8, which is 24. What do I times 10 by? I times it by 4, so I times the top by 4. And that gives me 28 over 40. Now what we can do is have a look and see which one is the biggest versus the smallest. Okay, so all I have to do here is compare the top numbers. So I look for the smallest top number, which is 22 over 40. But keep in mind, I'm ordering the fractions that they give us. So 22 over 40 is my smallest fraction. So that's going to be 11 over 20. So again, make sure you write it in its original form. So then what I like to do is I like to just cross out the one that I've done so I don't get confused. The next smallest value is 24 over 40, which is 3 over 5. So that'll be our next one. The next smallest one is 25 over 40, which is 5 over 8. The next smallest one is 28 over 40, which is 7 over 10. And lastly, we have 3 over 4 because it's the only one that's left. So again, students tend to make mistakes in this because they try and do it without making the denominators the same. So again, just as a recap of what we did, we made the denominators the same, then had a look at the numerators and saw which number was smallest, and then kept eliminating from there. That's all you have to do. And the last part of this, so whenever I have a slightly smaller bold text, that tells you what paper this is from, just so you can find the question. and this is for the inequalities. So one of the most famous use of inequalities is solving algebraic expressions. So if we have a look at this, the crocodile always goes for the bigger side. So what that means is that in this case 5x plus 6 is bigger than 3x plus 15. Okay, so whichever side this crocodile's mouth is looking at, that is the bigger side. So what this is saying is 5x plus 6 is greater than. Okay. If it was facing the other direction, that means it's less than whatever's on the left-hand side. So to solve this, you treat it as if it's an equal sign. Okay, so sometimes I like to tell people just make it equals. So 5x plus 6 equals 3x plus 15 and solve it like that. Or you just treat it as if it is an equal sign but still write it as greater than. So again, I look for the side that has the smallest number of x's. That's this side, so I want to get rid of 3x. To get rid of 3x, so it's plus 3x, so we minus 3x from both sides. That gives me 2x plus 6 equals 15. So that means I want to get rid of the numbers from the left-hand side, so I want to minus 6 from both sides. And 15 minus 6 gives me 9. So that gives me, divide both sides by 2. And we get x equals 9 over 2, but we're not done. Since I changed it from a greater than sign, I need to change it back. So I just replace it as 9 over 2. Literally nothing else changes, and that's 3 marks. Not too bad, I think. The next thing they like to do is represent inequalities on number lines. So what I'd like to, as a reminder, when it's filled in, it means it's equal to. And when it's hollow, it's not equal to. So what this is saying is it's all the values in between 2 and 5, okay? So what we do is we first write 2 and we write down 5. And in the middle we always have x, which is our unknown number, okay? Now what we need to do is decide how the inequality looks. Well, it's always going to be like this, because x, if we look at this half of it here, x is less than 5, right? Because it's smaller than 5. And it's greater than 2. However, it's also equal to 2, so we need to put the little equal sign here. But since this is hollow over the 5, it's not equal to, so we don't need to put the equal sign. Okay, so 2 is less than equal to x, which is less than 5. So it's between 2 and 5. The next kind of spec point that you need to be able to do is to add, subtract, multiply and divide integers, decimals, fractions and mixed numbers. So let's start with integers. An integer is just a whole number. Okay, so it doesn't have a decimal, it doesn't have a fraction associated. So let's start with adding. Let's say we were adding 132 plus 46. You might be able to do this in your head, but keep in mind that some integers are going to be quite big, so it's hard to do in your head. So what you need to do is use the column method. Okay, so 2 plus 6 is 8, 3 plus 4 is 7, 1 plus 0 is 178. Okay, so that should be hopefully quite familiar. Subtracting. Again, if we give ourselves a number, let's make it a bit more tricky. 421 minus 256. Let's have a look. You put the bigger number on top, or the left-hand number on top. Next number below. Again, ask yourself, can you do 1 minus 6? No, it's too small. So what you do is you borrow 1 from the left, so that 2 becomes a 1, and this 1 becomes an 11. 11 minus 6 gives me 5. Now can I do 1 minus 5? Nope, it's too small. So you borrow 1 from the left. Now it's 11 minus 5, which is 6. 3 minus 2, which is 1. Hopefully that is fairly familiar to you. Next, what we're going to do is do multiply. And again, we're going to be using the column method. So let's do 46 times 21. So again, you'd put the 4, the 6, And again, make sure you space out your work. Okay, so if you notice, all of my numbers are quite spaced out because a lot of the time students know how to do this, but what they do is when they squish their work together, they end up adding in the wrong columns and multiplying in the wrong columns. Also make sure that your place values are correct. So the 2 has to be above the 6, the 3 above the 4, and so on. Some students will put 46 where the 4 is under the 1 and 6 is under the 3. Not correct. Okay, so for this, we start with the 1, and we do 1 times 6 is 6, 1 times 4 is 4. So you always start from the right-hand number here and multiply by the other 2 numbers there. Now when we move over to the 2, we have to add a 0 because that 2 is in the tens column. 2 times 6 is 12, so we write the 2 and then carry the 1. 2 times 4 is 8, add the 1 is 9, and then what we do is we add the 2 values that are left, 6, 6, and 9. So that's everything you need to do for integers except division. So division tends to be the most tricky one. But again, you can use something like the bus stop method to help you out. So if you want to do 7 divided by, the wrong way around. So if we want to divide by 7, we'd put the bus stop method here, and we could do something like, let's say 350. Okay, so the question would be 350 divided by 7. How many 7s go into 3? The answer is 0. The remainder 3. How many 7s go into 35? The answer to that is 5. How many 7s go into 0? The answer is 0. So our final answer is equal to 50. Okay, so again, that's fairly standard stuff. You need to be able to do this without a calculator, and with a calculator, of course, because don't forget you have a non-calculator paper. The next one is decimals. So with decimals, it's actually very, very similar. So with decimals, adding is identical. Okay, so if we wanted to do adding, let's pick 2 decimals, 1.37 plus 2.56. Again, we want to write these such that the place values are correct. So 1.37, 2.6, adding. And then again, we just add from right to left. 7 plus 6 gives me 13, so 3, carry the 1. 5 plus 3 is 8, plus the 1 is 9. 2 plus 1 is 3. Done. Nice and easy. Subtraction works in the exact same way. So if we have something like 3.42 minus 1.37, what we do is we put again 3.42, subtraction sign. Can we do 2 minus 7? No, so we borrow 1 from the left. 12 minus 7 is 5. 3 minus 3 is 0. 3 minus 1 is 2. So we get 2.05 as our answer. Okay, so that is fairly self-explanatory. It's the same as using integers. However, when we do multiplying and dividing, it gets a bit more interesting. So let's start with multiply. Okay, so let's say I wanted to multiply 34 by 1.2. Now, we can't just go ahead and do this in the column method the same way we did in integers, because the 0.2 acts in a slightly different way. So what would be really convenient is if the 0.2 wasn't there. Okay, so what I need to do is think about how can I change this so that the 0.2 isn't there. And we can always times. So if I times this number here by 10, my question now becomes 34 times 12, which I'm more than capable of doing. Okay? But what I need to do is remember at the end to divide by 10. So because I've times by 10, divide by 10 at the end. Okay? Likewise, if you times by 100, you divide by 100. Times by 1,000, divide by 1,000, and so on. Okay? And if you times both numbers by 10, you divide by 100 at the end, or you divide by 10 twice. Okay? So let's work out how to do 34 times 12. 2 times 4 is 8. 2 times 3 is 6. add a 0. 1 times 4 is 4. 1 times 3 is 3. Add these up, we get 8. 6 plus 4 is 10. 408. That's not quite right. We need to divide by 10 at the end. To divide by 10, I have a decimal point here. I just move it over here. So my final answer is 40.8. Nice and easy, hopefully. Okay. Now for dividing, it is a similar situation. However, you can do something a bit more interesting. Okay. So let's say we wanted to do 40 divided by 1.5. Okay. Now I can also write this as a fraction. And once again, I want to get rid of the 0.5. I don't want a decimal. So I might think of doing the exact same thing we did in multiplication. If I times this by 10, the decimal goes away because it moves once over to the right. Now with a fraction, if you remember from the previous point we went through, whatever we do to the bottom, we have to do to the top. So it's the exact same as doing 400 divided by 15, which I can do. Okay? And the way I can do that is I can do 15, 400, 15 into, so because it won't go into 4, right, we can put a 0 here and put 4 there. How many 15s are in 40? Well, there's 2, remainder 10. How many 15s are in 10? Well, it would be 0, and then what we can do is add on here. What would be the remainder? It would be 10. 15s into 100, and so on. We can keep going on, okay? And keep going on to get our answer. And then all we need to do, and at the end, we do not need to divide. The reason for this is because we times the top and the bottom by 10, the overall answer is going to remain the same. Okay? So it doesn't actually make any difference whatsoever. Okay? Perfect. I hope that all makes sense. So now if we move on to the next part, which is fractions and mixed numbers. Fractions and mixed numbers are actually identical. So let's just quickly go through fractions. Again, if we want to do adding, to add two fractions, again, let's pick two fractions. We can only add fractions if we make the denominator the same. Okay, so what we need to do is find out what the smallest number we can make 3 and 4 into. Well, in the 3 and 4 times table, the smallest number that appears is 12. So how do I make 3 into 12? I times it by 4. How do I make 4 into 12? I times it by 3. So then that becomes 4 over 12 plus 3 over 12. And now to add these together, all I need to do is simply do 4 plus 3, which is 7 over 12, and then simplify my answer if it is indeed possible, which it isn't in this case. Nice and easy, I hope. With subtraction, let's pick two fractions again. Let's pick 7 over 15 minus, let's do 3 over 5. Okay. So with subtraction, we also need to make the denominator the same. This is vitally important, okay? So what's the smallest or lowest common multiple of 15 and 5? Well, it's 15. So I don't need to touch the first fraction, but I can times the second one by 3 in order to get my answer. So that would be 7 over 15 minus 3 times 3 is 9, 5 times 3 is 15, so 7 minus 2 would give me negative 2 over 15, and that's it. For multiply, you'll be happy to hear you don't have to change the denominators at all. So if we do, again, let's pick two numbers, 2/3 times 3 over 4. All you need to do is multiply the top numbers together. so 2 times 3, which is 6, and multiply the bottom numbers, 3 times 4, which is 12, and then don't forget to simplify your answer. So I can divide the top and bottom by 6 in order to get 1 over 2. Okay, so again, always remember with fractions you need to simplify your answers. Lastly, we have division. Now division works a bit more interestingly, so let's again pick two numbers. Let's do 3 over 4 divided by a half. What we're going to look for is the KFC method. Okay, so KFC, K stands for keep. So what we do is we keep the first fraction the same, nothing changes it. The F stands for flip, we flip the second fraction, so 3 over 4 now becomes 2 over 1 here. And the C stands for change, and that means you change the divide to a multiply. Okay, so again KFC, some people say KCF for reading it left to right, like keep, change, flip, but I prefer KFC because it sounds better. And then you multiply them together as if you're doing the previous question. 3 times 2 is 6, 4 times 1 is 4, we can divide the top and bottom by 2, 3 over 2. Remember, when you're simplifying fractions, one of the easiest things you can do is just to keep dividing by 2 until you can't anymore. So if they're both even numbers, you can always divide by 2. And if you can't, then choose 3, and then choose 5, and then so on. Okay? But if you can divide by 4, you can also divide by 5. Okay. So, lastly, it needs to also be mixed numbers, right? So again, this is a very long section, but it's not too tricky. Hopefully you've had a lot of practice doing this. With mixed numbers, the only difference is you change. So with mixed numbers, you change to improper fractions, proceed as normal. Literally the only difference. However, they tend to expect the answer back as a mixed number. Okay? So you change to improper fractions, do everything as per usual, and then change back into a mixed number. So just as a bit of a recap, a mixed number, let's say it would be 3 and 1/2. To convert that into an improper fraction, you do 3 times 2, which is 6, plus 1 is 7 over 2. So all you do is you take the big number, multiply it by the denominator and add the numerator. 3 times 2 plus 1 is 7, and then over the original part. Now if you want to change back into a mixed number, what I ask myself is how many 2's go into 15? 2, 4, 6, 8, 10, 12, 14, that's 7. So I write a big 7. And how many's left over? That's 1 over the denominator, and you're done. Okay? And then you just proceed as per the usual. So hopefully that was all fine. Again, that's one big chunk of the numbers topic that we're finished with now. So what we should do next is place values. So place values are very, very important in terms of doing calculations and also reading numbers properly, which might sound a bit condescending. But essentially, they tell us exactly what each digit represents. Okay? So what you should hopefully be aware of is the 2 here is in the hundreds column, the 0 is in the tens column, and the 4 is in the units column, and then this is in the tenths column. So this 2 doesn't represent 2, it represents 200. 0 tens, so 200, and 4 units, 0.7. So the value of the 7 isn't 7, it's 0.7, or both answers are equally valid, 7 tenths. Okay? Both answers are completely valid in your mark schemes. Okay? So again, hopefully that's relatively okay. If you're ever confused about place value, just read the number. Okay? So if I give you a number, something like 3, 4, 5, 7, and I'm not sure what the 3 represents, well, read it out. 3,457. 3 thousands, 4 hundreds, 50, so 5 tens, 7 units. Okay? Just read it out loud and you'll find that you know how to do it. Okay? Or in your head if you're in an exam, of course. Next question says, write down a 5-digit number. That's 3 as its thousands digit. You can only use the digit 3 once. So what I like to do in questions like this is I like to draw boxes. Okay, so there are 5 boxes and then I can put the number in here. So let me draw that a little bit bigger. Okay. So this is going to be my 5-digit number, right? These are all blank spaces. Now, if I were to write this out, I know that this is the units, that's the tens, that's the hundreds, that's the thousands, and that's the 10 thousands column. So we're looking for a number that's in the 10,000s, okay? Now the thousands digit has to be 3, so let's fill that in. And now I just fill in the rest with any numbers I like that isn't 3. So my number here is 13,245. Fairly standard. And again, with place value. So place value can come up in a lot of different forms, hence why we have a bunch of different questions on this, even if you might find it a bit easy. Write the number 5.3 million in figures. Okay, so what that means is in digits. So exactly how I've written it here. So 5 million, now a millions number is going to have whatever this digit is, so a 5, and it's going to have 6 numbers after it. So 5.3, so I'm going to put the 3 here, and then I'm going to fill the rest with the zeros. Okay, so I said there should be 6 digits, so we've already used 1, so 1, 2, 3, 4, 5, 6. And we put commas every 3 digits. And that's it, 5.3 million in figures. Not too bad. We have 4 number cards, 5, 7, 2, and 3. Write down the largest 3-digit number that can be made. So, this is, again, it's a really good way of testing your understanding about place value. Okay? So, if we want the biggest 3-digit number, we want the first digit to be the biggest number possible. Okay? Because the bigger this first digit is, has the biggest impact on the number. If I change this from a 5 to a 6, it becomes 6 million. If I change this 3 to a 6, it's 5,600,000. Which one's bigger? The 6 at the front, right? So what we do is we pick the biggest number, 7. Then we pick the next biggest number, which is 5. Then the next biggest number, which is 3. So if you want to write the biggest number, you go from left to right using the biggest digits you have. So 753. If they wanted the smallest number, then what you do is you go from smallest to biggest. So you pick the smallest number, then the next smallest, then the next smallest. Easy peasy. Speaking of, arrange the cards to give the smallest possible answer to the sum. This is actually a bit tricky, because what some people do is they put the smallest 2 digits, then the next smallest 2. So they'd pick maybe 23 plus 57. Okay. Now 23 plus 57 gives 80. What you can do instead is you pick the smallest number and the biggest one after that. So 2, 7, then 3, 5. Now 27 plus 35, 5 plus 7 is 1, 62. It's a lot smaller. So it's a bit of a tricky question, but what we want is the first digits of both of these numbers to be as small as possible. So 2 and 3. Okay? So that's how I got the 2 and the 3 here. Smallest digits first, because that has the biggest impact on the number, like we just said. Now, how do we make the smallest units possible, right? Well, if this is a 20, then I want to put the biggest number with the 20, because that has the smallest effect. 27 compared to 37, 27 is a lot smaller. So smallest, biggest, smallest, biggest. Oh, good. So relatively short not chapter, like a sub-chapter. Hopefully that's all okay. Again, there's tons of practice questions available for you. Inverse operations. Okay, one that's super quick. Inverse operations means that you should be able to understand that adding and subtraction are opposites of each other. So for example, if I do 25 plus 5 gives me 30. To go from 30 to 25, I do the opposite, the inverse operation, which is minusing 5. Likewise, you have times is opposite to divide, and divide is opposite to times. The last one would be using a power and then the rooting. So a power is opposite to a root. So for example, squaring, opposite to square rooting. Cubing is opposite to cube rooting. Taking the fourth root is opposite to power of 4 and so on. That's literally it with what they can ask you. There are inverse functions which come up a bit later, but that isn't part of the numbers topic, just in case you're wondering why I haven't included it here, okay? That's not the numbers topic. Next is BIDMAS. Now, depending on kind of what school you go to, what country, and etc., you may have seen this written as BODMAS or PEMDAS or anything else. It's all the same thing, okay? So BIDMAS just tells you what order you should do something in. So what I mean by that is, let's say you had 5 times 5 minus 3, okay? So there are two ways of looking at this, right? Either I do 5 times 5 and then minus 3, or I do 5 minus 3 and then times 5. They give me completely different answers, right? 5 times 5 is 25, minus 3 is 22. 5 minus 3 is 2, times 5 is 10. So how do I know which way to do things? Well, that's where BIDMAS comes in. BIDMAS says that you should do things in this order. So let's write it out. B is for brackets. So if you ever see a bracket in a calculation, you do the bracket first. Then you do the indices. Indices are things like 3 squared. So if anything has a power, that's an indice. Or if it has a square root, that also counts as an indice. D is for division. M is for multiplication. A is for addition. S is for subtraction. Okay, so for example, PEMDAS, P is for parentheses, which is the same as brackets. E is for exponents, which is the same as indices. So it is literally the same thing. So the answer to 5 times 5 times 3, well, let's have a look. What turns up first, the multiplication or subtraction? Well, the multiplication does, so I do 5 times 5, which is 25. Then I do the subtraction, which is 22. Okay. Now, the one exception to this, which kind of tricks people, is if you have a fraction. So let's say I have something like that. Okay. Doesn't affect it too much in this case, but let's say we also had like a multiplied by 3 and a minus 4 here. Okay. What do you do first? This division comes first, right? Like the division is before all of these. So do I divide first? No. You need to do the numerator and denominator separately, find out what those are, then follow BIDMAS. Okay, so I'd still do BIDMAS for 3 plus 2 times 3, right? So I do 2 times 3 first, because multiplication comes first, then add 3. Then I do the 4 divided by 2 minus 4, so 4 divided by 2 is 2 minus 4. Then I simplify the fraction, okay? So the fraction bit, you do the numerator and denominator separately, okay? That's it for BIDMAS. So we've done 2 chapters in about 2 minutes. That's pretty good. Let's move on. This is a big one, okay? This is a really big one. So prime numbers, factors, multiples, common factors, common multiples, highest common factor, lowest common multiple, prime factorization, index notation, product notation, and unique factor theorem. Whew. Hell of a lot. So prime number, let's start with something that's relatively easy. It's a number that has 2 factors. Itself and 1. So basically, it can only be divided by itself and the number 1. So you should be able to recite the factors from, well, realistically from 0 up to about 100, but you should be able to determine whether or not something is a prime number just from using your knowledge of things like times tables. So again, starting from the beginning, we have the number 2, it's only divisible by 2 and 1. It's also the only even prime number. Then you have 3, so on. All of those numbers can only be divided by themselves and 1. Okay, and again, this goes on forever. If you notice, they get further and further apart as well. Okay, a multiple is just a number that appears in another number's times table. Might sound a bit weird, but for example, 8 is a multiple. So what times tables does 8 appear in? It's 2 and 4. Okay, so that's all it means. So 16 is a multiple of 2, 4, 8, so on. So common factors, so the word common means it's for multiple numbers. So for example, a common multiple of 2 and 4 would be 8 and 16, because 8 and 16 appear in both the 2 and 4 times tables. With a factor, which is something we haven't gone through yet, a number that divides into another number without a remainder. So basically, is the number divisible by that number? It's a factor. So again, 4 is a factor of 4, 8, 12, 16, and so on. Because 4 divides into all of those numbers without a remainder. That's all the maths definitions, so all the writing we're going to do for that section. The unique factorization theorem just says that any number can be written as a product, so a multiplication of prime numbers. Okay, and we're going to get onto that when we do prime factorization. Okay, so work out the highest common factor of 75 and 105. How the hell do we do this? Well, what we do is we write both of these numbers separately and we do a factor tree. Okay, so these numbers both end in 5, so I want to divide by 5. Right, 75 divided by 5. To divide any number by 5, divide it by 10, so 7.5, then double it, so 15. Then I want to do 3 and I want to keep going until I only have prime numbers. And if you have a look, 5's prime, 3's prime, 5's prime. Done. 105. So again, let's divide by 5. Divide it by 10, that's 10.5. Double it gives me 21. Then I'm going to do 7 and 3. Now, what numbers are common between both of these? Well, we have a 5 and a 5. So let's do 5. We also have a 3 and a 3. So my answer for the highest common factor is 5 times 3, which is 15. Okay? Simple as. You only look for the common numbers, but beware to not double count. So there's 2 5s here, but only 1 5 is common. Okay? If there was another 5, we would times by 5 again, but there isn't. Okay? I think that's fairly okay. Yeah? Lowest common multiple, couple ways to do this, but for this one is we're looking for the smallest number that appears in the 5, 15 and 25 times tables. So it's one of these numbers. Well, I know it can't be 5 because 5 is smaller than 15 and 25. It can't be in its times tables. Okay, let's look at 45. Well, it goes into both of these two. But does 45 divide by 25? Nope, so it's not that one. 75? Well, it's definitely divisible by 5. 75 or 15, 30, 45, 60, 75, it does. 25 or 25, 50, 75. So it is definitely this one. Okay, so we're just going up in the times tables. Lastly, prime factorization in index form. So what we do again is we're going to do a little factor tree. So let's think of a number we can divide 200 by. Well, 2 makes sense. And again, we circle the prime numbers. I can divide it by 2 again. I can divide that by 2 again. So again, just keep dividing by 2. I can't divide that by 2 anymore, but can I divide it by another prime number? Well, 5 works. So 200 is equal to 2 times 2 times 2 times 5. And if you were to use it on a calculator, you'd find that that is indeed true. And what we can do here is, this is just in product notation, but in index notation, what we do is we write out all the different numbers we have. So we have a 2, but how many copies of the 2 do we have? Well, we have 1, 2, 3 2s, so that's 2 to the power of 3. Then with the 5, we have 5 and 2 copies of the 5. That's all index notation is. It's a shorthand way of writing this. So if you're lazy like I am, this is actually going to be really useful for you. Okay? And again, so this just reminds you of what paper this came from. Next thing is systematic listing strategies. And for the higher paper specifically, the product rule for accountants, everything up to now has been foundation and higher. Because again, this is the core maths you should be able to do for everyone, okay? Now, we also have the product rule. We'll get onto what that is in a second. So let's just go through some questions, right? So there are 12 boys and 15 girls. 1 boy and 1 girl is selected to represent the class on the student council. Work out the total number of ways of choosing a boy and a girl. Well, let's think about this, right? We have 12 boys and 15 girls. Now, every 1 boy can be matched with 15 possible girls. And then the next boy can also be matched with any of the 15 girls, right? And the next boy can also be matched. So in other words, we have 12 boys and 15 girls. So we have 12 times 15 combinations that we could potentially have, okay? And 12 times 15 is 180, okay? So again, just remember that 1 boy can match with 15 girls, and there are 12 boys, so 12 times 15. Simple as. Now, the next question is slightly more interesting, and you have to apply your logic. And again, with these kinds of questions, very, very easy for students to lose marks because they make a mistake. 52 cards in a deck, standard. Peter's going to give 1 card to Casper and 1 to Kelly. How many different ways are there of doing this? Well, first of all, how many cards could Casper get? Well, it's one of 52 cards. Okay? Now, each one of those cards can match with the card that Kelly gets. So how many cards can Kelly get? It's not 52. 1 is with Casper. So it's 51 that Kelly can get. So Casper, Kelly. Now, every 1 card that Casper gets can match with 51 cards that Kelly gets. Right? So, for example, if Casper gets the Ace of Diamonds, yeah, Kelly can get any other card, all 51 other ones. Then if Casper gets the 2 of Diamonds, Kelly can get any of the other cards. So again, just like in the previous question, we multiply this together. Okay, so again, if you just use a calculator, this kind of thing would normally appear on a calculator paper. You get a total combination of 2,652. Pretty damn big. Hope that all makes sense. Okay, next bit, again, it's fairly standard. It's just something that you have to know. So what you should be able to do is you should know all of the squares up to 10 squared. So, well, realistically, it should actually be, I've seen it go up to 13 squared, right? So you should be able to do 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, right? But not just be able to calculate it, you should recognize it. So for example, instead of writing 12 squared, if they write 144, they can ask you in a non-calculator paper what the square root of 144 is as part of a calculation, and you're expected to be able to say it's 12. You're expected to be able to recognize square numbers. Okay? With cube numbers, it's slightly smaller what they ask you to go up to. Some people say go up to 9, but the cubes that I've seen them come up are obviously 1, 2, 3, 4, 5, and also 10. Okay? So some people say go from 1 to 10. I've only really seen 1 to 5 and 10. Okay, so you should be able to recognize them. So again, that 5 cubed would give you 125. You're expected to work both ways. Okay? In terms of that, it's really about recognition. Now, what I will say is with the number 2, they expect you to know what, for example, they expect you to recognize that the 5th root of 32 is 2. Okay, so they can expect you to do that. Now, this may seem very arbitrary in the sense that it's a bunch of different numbers, is a bit confusing. What I will say is if you do enough practice, you'll see what numbers come up. Okay, so for example, the 5th root of 32 or the 6th root of 64 is 2. So they don't ask you literally any of these numbers, and I wouldn't advise necessarily memorizing them. What I'd recommend you do is just do enough practice that you know them off the top of your head. Okay, and you can recognize them fairly easily. The only ones I would bother memorizing are the square numbers up to 13 squared, which, not too bad. You can always work them out anyway. Okay. In a similar vein, they can ask you about calculating with indices, in particular, fractional indices. So first of all, 7 to the power of 0. This is one that students always forget. They usually write something like 7. Not correct. Anything, and I mean anything, to the power of 0 is equal to 1. Doesn't matter. So x to the 0 equals 1. 1, whatever that number is to the power of 0 equals 1. Doesn't matter. If anything has a power of 0, it is equal to 1. Anything at all. No exceptions, okay? So in this case, my answer is 1. Okay? Fractional indices get a bit more exciting. Okay? So what you should be able to recognize is that if we look at this as a... I've just made the power a fraction, right? It's already a fraction, but I've expanded it. The bottom number, so denominator, obviously, is your root. The top number is your actual power. Now, it's always easier to do the denominator first. Always. Okay? Because if you do 32 cubed and then trying to find the 5th root of that, you're not going to have a good time. So what I want to do first is work out the 5th root of 32. And conveniently, I told you what that was. It's 2. So now this becomes 2 to the power of minus 3. So what I do now is I do 2 cubed. Ignore the negative for now. Yeah? So... okay. So 2 cubed, well, that's 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So that's 8 to the power of minus 1. The negative just flips it. So instead of 8, I have 1 over 8. If I had 3 over 2 to the minus 1, I would flip it 2 over 3. Okay, the negative just flips it. Okay, again, we're getting there. We're doing really well. We've got over halfway through the whole number section. So just as a reminder, the AQA has 6 sections. Numbers is probably the most important one, and it's representative of quite a few marks. But if you're getting this so far, really good job, okay? We've just got a bit further to go, and we'll have covered everything. Calculate exactly with fractions, pi, simplify surds. So what they sometimes do is in a non-calculator paper, they'll have something like, and they'll have 4, and it say calculate. It could be the circumference or rate or area. And what they expect you to do in a non-calculator paper is to recognize that would just be 16 pi. That's it. Super easy. Basically, I mean, you're being lazy, right? You don't have to work it out. You don't have to times by 3.14. You leave it in terms of pi. You can do the same thing with fractions. Okay, they expect you to be able to leave your answers in fractions rather than doing long decimals. This is normally in the non-calculator paper for obvious reasons. Simplifying surds, well, I have an example question, but you should also be able to recognize that, for example, with the square root of 45, you can write that in terms of 2 separate numbers. So 45 is the same as doing 9 times 5. And you need to pick a square number. Okay? So a number that can be square rooted. That's the same as doing 9. Square root of 9 is 3. So that is something they expect you to do. You need to simplify your surds. Okay? And again, in the non-calculator paper, they'll expect you to simplify every surd you have. So again, if it can, try and break it into a square number and a non-square number. You're golden if you do that, because then you just need to square root the other number. If not, then you can't simplify it and you're good. So, this last bit says rationalize the denominator. Okay, what does that mean? Well, surds are irrational numbers, which means they're infinitely long. So if you type in root 2 on your calculator, it comes up with a ridiculously long number, okay? Because it's irrational. So you can't have surds in the denominator. It's illegal, okay? So if you see a surd in the denominator, you have to rationalize it. Get rid of it. So let's see what we do here. Well, the first thing I want to do is, I'll leave the 150, that's fine. And it says show that it simplifies to an integer as well, so a whole number. Is I do root 2 times root 3. Timesing 2 surds is nice and easy, you just get root 6. Pretty good. Now, this root 150, I probably want to actually get rid of that first, or at least simplify it. So what I can do is find a square number. So look at 150, that's divisible by 25, so I'll make that root 25. And that would be 6 minus root 6 over root 6. And again, we're just simplifying this fraction at the moment. So that becomes 5 root 6 minus root 6 over root 6. Okay, so now how do I rationalize a denominator? Well, if I want to get rid of a square root, all I do is I times by the exact same square root. Because if you have the square root of a number times by the square root of the same number, it just becomes the number. Okay? Remember, with a fraction, whatever you do to the bottom, you do to the top. So now that becomes 5. Now root 6 times root 6 becomes 6. So we have 5 times 6 minus root 6 times root 6 is 6 over root 6 times root 6, which is 6. 5 times 6 is 30 minus 6 over 6. That's 24 over 6, which of course is 4, which is indeed an integer. We're getting there. We're almost there at the end. Next bit, hugely important topic, especially if you want to do any sciences in the future or anything with big numbers. So what they expect you to know is that standard form, which is a times 10 to the power of n. A has to be between 1 and 10. Okay? So 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's it. And n is just some integer. So if we were to work out 2,000 times 70,000, give your answer in standard form, you might be aware that what you can do is just do 2 times 7 is 14, followed by the 4 zeros that it gave you. and then all you need to do is add on the 3 extra zeros. Right? So I did the 2 times 7 first. That gave me 14 with 4 zeros. Then I just added on the 3 zeros there. So for this to be a standard form answer, the first digit has to be a number between 1 and 10. So what I need is the decimal point is here. I need the decimal point to be between the 1 and 4. Because before the 1 and 4, it becomes too small. Afterwards, it's too big. So I have 1.4 times 10. Now, how many times did I have to move this decimal point to get it back to where it started? Well, I move it once, twice, 3, 4, 5, 6, 7, 8 times. So 1.5 times 10 to the power of 8. Okay? And lastly, you need to be able to calculate with standard form. So when you're dividing or when you're timesing, you can just do this division first and this division afterwards. Likewise, if you're timesing, you can do the first numbers times together, the second numbers. So 1.8 over 3. So what we could do is times top and bottom by 10, or whatever you wanted to do. So I times that by 10, I get 18 over 3, which is 6. So I divide that by 10, so my actual answer would be 0.6. Now when I'm dividing, I'm just using my rules of indices. 10 squared divided by 10 to the minus 1. So I'm doing 10 to the power of 2 minus 1. So I get 0.6 times 10 to the power of 3. Now this 0.6 is not between 1 and 10. So I need to move this over 1 to get 6. And to do that, I need to reduce the power here by 1. Okay, so if you think about it, what I'm doing is I'm taking one of the times 10s and timesing my first number by 10. So I need to divide this one. So if I times this side by 10, I divide this side by 10. Okay, because otherwise it won't be the same number. Okay, with this next one, we have to do converting between fractions and decimals. That is pretty much the same as doing the recurring decimals into fractions as well. So if I want to change this fraction into a recurring decimal, it's the same way as what I'll do is when I convert a fraction into a decimal. What I do is I do the good old-fashioned bus stop method. However, I'm going to expect to have a bunch of zeros, okay? How many 6 are in 5? 0. Move that to the other side, so now we have 5 here. How many 6s are in 50? So 6, 12, 18, 24, 30, 36, 42, 48. So 8 remainder 2. So 0.8. How many 6s are in 20? 6, 12, 18. So 3 remainder 2. How many 6 are in 20? 3 remainder 2. You can probably see what's happening now. It's going to keep being 3 remainder 2 forever. So in other words, it's just equal to 0.83 recurring. And that's the same way you change a fraction into a decimal. You just do the division using bus stop method. So that is from your 2021 paper. Now we're going to be doing something like this. So this is changing recurring decimals into fractions, something that's super exciting. So if I say that x is equal to my number, what I need to do now is get rid of the recurring decimal. So what I do is I times this by however many digits are before the 7, the recurring number. So 1, 2, I times it by 100. Times by 10, times by 10 again. That gives me 347.7 recurring. The next thing I do is I times it by a certain number that will make the 7 recurring be in this first decimal place, which in this case is 10. The reason why we do that is we want to subtract these two to get rid of all of the recurring decimals. Okay, so the first thing you do is you times by however many 10s you need to make the 0.7 in the first decimal place. So in order to get rid of it, so we have two numbers before the 7, which is recurring. So we times by 100. Then the next thing you times by is however many it takes to make that into the first decimal point, 10. Now if I do 100x minus 10x, that is equal to 347.7 recurring minus 34.7. So that gives me 90x. So the 7 recurrings go away. So we're just doing 347 minus 34, which would be 313. That's it. Divide both sides by 90. So, funnily enough, they actually do give you a bit of a hint here. Okay, I know I'm going to be doing 100 minus 10 because that's the only way I can get 90. Okay, so again, just to take from the top, I saw that there were two numbers before, two digits before the recurring digit, so I times by 100, so times by 10 twice. Then I need to get rid of that decimal, which is in its first place, so what I need to do is times it by 10 because that would make the recurring decimal in the first decimal point. Then I just subtracted. Again, by looking at 90, you can also see you're going to be doing 100 minus 10 at some point, so that's also a way to do it. Okay. And changing ratios into fractions and vice versa. So in terms of exam questions, there isn't really an exam question on it. Instead, it's part of a question. So if I say, for example, we have Harry and Steve, and they're sharing sweets in the ratio of 3 to 2, what fraction does Harry get? Super easy. I take the number I'm interested in, so in this case, Harry, and I divide it by both sides added together. Okay, easy. Now, if there's 3 people, so A to B to C, and it's 1 to 2 to 3, for example, let's say we wanted the fraction of B, we would take the number we're interested in, B, and then add all of the other sides. And that's it. Okay. Likewise, you should be able to do this backwards. Okay. So for example, you should recognize that 3 over 2 is going to be a ratio of, so actually let's do 2 over 3. Is going to be a ratio of the 2 that we're interested in, and 2 plus what gives me 3? 1. 2 to 1. Simple as. The next part is interpreting fractions and percentages as operators. So if I say half of £50, you should be able to recognize that this thing here is an operator. So what I mean is I'm actually applying this. So half of means multiply. So it just means I'm doing a half times 50. So 50 over 2, £25. In the same way, that if I say 25% of 40, you should be able to tell me what that answer is. So 25%, you can do it as a fraction. So that's 25 over 100, which is equal to a quarter. And again, of means times. So a quarter times 40, we get 40 over 4, which is 10. Simple as. You just need to be able to interpret that. So if they ever give you like a third of 30 goes to charity, you should be able to do a third times 30 and work out your answer, okay? That's just something that they kind of expect you to be able to do. Cool. And next, standard units of mass, length, time, money, etc. Convert between metric quantities. Imperial to metric are given. So simple, metric is what you use in science. Okay, so for length, you need to know millimeters, centimeters, meters, kilometers. Okay, so you should also know that to go from this. So how many millimeters in a centimeter? Well, it's 10. So you divide by 10. Centimeters to meters. There's 100 centimeters in a meter, so you should be able to divide by 100. There are 1,000 meters in a kilometer. Divide by 1,000. And you should be able to go both ways, convert between meters and millimeters and centimeters and kilometers and everything. With mass, slightly fewer options. All we have is grams and kilograms. And to go from grams to kilograms, you just divide by 1,000. For time, again, not really many options. It's the ones that you should be familiar with. Seconds, minutes, hours, days, and weeks as well. So you should know that there's 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 7 days in a week. Hopefully that's fairly standard. And then with money, well, the only standard unit for money, or basically currency, is pennies and pounds. And again, you should know that there are 100 pence in a pound. Everything else is going to be given to you. So for example, if they say, so imperial units are things like pounds, inches, miles, things like that. They give you the conversions. You don't have to worry about that. You should also know that for area, you have to, so for example with area, again you have millimeters squared, instead of dividing by 10, you're dividing by 10 squared. Instead of dividing by 100, you're dividing by 100 squared. And dividing by 1,000 squared. And the reason for that is because of this squared here. So with volume, you're going to be dividing by, you probably can guess. So again, millimeters cubed, centimeters cubed, meters cubed, and kilometers cubed. You're going to be dividing by these values cubed. And so on. And again, any other things they may give you, again, in terms of imperial units, again, inches squared and whatever, they will give you the conversions for them. Okay. And last 2 points are to do with estimation and degrees of accuracy. So, whenever it says estimate, using approximations to estimate or estimate, you round everything to one significant figure. That's it. Don't worry about anything else. So if I'm doing this, so again, this turns up in a non-calculator paper, round everything to 1 SF. So, square root of 97, no, it's square root of 100. 2.014, nope, it's 2 cubed. Again, 1 SF. Now 0.49 rounds to 0.5. There you go. Square root of 10 gives me 10. 2 cubed is 8 over 0.5. 18 over 0.5. Hopefully you know that that is basically just doubling the answer. Right? Because you're times top and bottom by 2, so if you're unsure about that, times top and bottom by 2, you get 36 over 1, so that's 36. That's it. Estimation, round to 1 SF. 1 SF, round to estimation. Okay? That's it. Estimation, round to 1 SF. Lastly, suitable degree of accuracy. You should be able to round to decimal places and sig fig. Most common are 2 decimal places and 3 significant figures. So let's say I get an answer of 141.37. What is that to 2 dp? Well, to 2 decimal places, what I do is, actually let's add another digit, is I go to the second decimal place and I look at the number next to it. If it's 5 or more, I make this number 1 bigger. If it's 4 or less, I keep it the same. It's 4 or less. So the answer is 141.7. 141.37. Now what about 3SF? Well, a significant figure is any figure that is not 0. So you ignore all the zeros, then you get to the first significant figure and you count from there. So 1, 2, 3, this is the value. Look at the number next to it. Is it 5 or more? No, keep it the same. 141. Simple as. Okay? Super, super easy. And again, the reason why there aren't always exam questions for this is because it's part of the question. They'll say, round your answer to 2 decimal places, round your answer to 3 significant figures, round your answer to the nearest whole number, etc. All you do is you use this method here, and that will be it. So hopefully that was all very useful for you, and you're ready to tackle the next section.